Hello everyone, welcome to EduDungeon. We are thrilled to announce that we are launching our first course, that is Let's Dive into C. It will be a C programming language course. We will discuss in this course that how the hardware works along with softwares to make the computers functional, and how the hardwares are made with basic electrical components like resistors, inductors, capacitors and transistors. And we will jump into the early computers to understand how the vacuum tubes worked together to get those early computers work. And the basic focus, the main focus of this course will be on the C programming language. We will deep dive into the C programming language and we will master it, and along with you will get to work with a hands-on project like developing games and daily tech products.
So as you can see, we are at the first slide of our demo lecture of Let's Dive into C. I am your instructor Shumit Roy. So let's move forward. So today's syllabus will be a simplified overview of basic electrical components like resistors, battery, capacitor, inductor, diode and transistors. Transistors are a bit much complicated, so we'll deep dive into that. After that, we will discuss about logic gates, and then we will discuss about two types of circuits like analog circuits and digital circuits. After that, we will jump into the introduction of computers. Here we will have some ideas like how hardware components are arranged in computers and how they actually function. After that, we will have some cool discussions. So wait till the end. So at the first topic, there are some prerequisites, some basic concepts of electrostatics. Yeah, you need to know some electric components and how they work, the functional like physical quantities. You have to know all of this. So let's just jump into that. At first we have electric field. What do you say? Electric field is just a force line due to some charge. To be precise, there are multiple force lines from a charge. Let's imagine we have a charge here and it's a positive charge. When we have a positive charge here, it emits some force lines from its, like it radiates multiple force line from us, forming a sphere around it. As you can see in this PPT, we have discussed that if it's a positive charge, it radiates force lines to all the directions, and these force lines are called electric field, you can say. And if we have negative charge, the force line just got reversed. If we have negative charge here, the force line just goes into it, inside it, you can say, like as directed in the PPT. For a negative charge, the electric field lines or the force lines are inward, and in the case of positive charge, the force lines are outward. So after that, it is a symbol of battery. It is a symbol of battery. Okay. Then the battery have positive terminal and a negative terminal. We all know battery, right? Yeah, obviously we all know. We all know batteries. They have one positive terminal and one negative terminal. So the positive terminal of the battery is called anode and the negative terminal of the battery is called as cathode. Okay. So how the electric field will form inside a battery? What I said, from a positive charge, electric field line radiates, and for a negative charge, electric field line just goes into it. So imagine both charge are present here at the same time. So the positive charge will emit or radiate its force lines, and the negative charge will capture those force lines. So we will get a electric field from positive charge to negative charge. Okay, as directed in this PPT, you can see the positive plate, anode, and the cathode, which is the negative plate. The electric field line is going from the positive plate to the negative plate, or you can say it goes from anode to cathode. Okay, now we get some idea of battery, and now we jump into the next segment: how charges act inside electric field. Like, we imagine we have a battery, and the battery's electric field is fixed, isn't it? Obviously the battery's electric fields are fixed. Like, can you interchange the positive and negative terminal of battery? No, you can't. Those are manufactured that way. So once we connect a circuit, the positive terminal and the negative terminal are predetermined, so we can't change them. In that electric field, the battery has its own electric field now. So in that electric field, if we place a charge inside that electric field, the charge will experience some force. As we mentioned earlier, that electric field lines are force lines, isn't it? So as electric field lines are force lines, then in an electric field line, if we place a charge, it can be a positive charge, it can be a negative charge. If we place a charge inside an electric field, it will feel some force, and positive charge and negative charge has this can have force applied on them, but in different direction. Let's see. In positive charge, the force will be applied as same direction as the electric fields are heading, and in the negative charge, the force applied on the negative charge will be just opposite to the direction of electric field lines. This is important concept. Just have a quick overview of this. External electric field are going this way, from this way to this way. External electric fields are going like this way. And if we place a positive charge in that external field, it will feel a force pulling it towards the electric field. You get it? Electric fields are going this way. If we place a positive charge here, it will also feel a force applying on it in this direction. And imagine if we have the external field line like this, and if we place a negative charge in this portion, the negative charge will feel a similar force but in opposite direction to the electric field lines. So the negative charge will feel force from this to this. Electric field lines are from here to here, and if we place a negative charge inside that electric field, it will feel force towards the opposite direction of the electric field lines. Now a cheat code for you guys. You can assume positive charge, where in this demo session where you will see positive charge, you can imagine that as high potential energy, and where you can see negative charge, you can imagine that as low potential energy. Okay, so now you may ask that what are potential energy? Obviously, let's take the example of a battery. A battery is there, it has chemical energy inside it, which is posing or converting itself into some potential energy that is transferred to the cathode and anode of that battery. And after that, from that cathode and anode, the energy transfers through the circuit and forming electrical energy. So as you see a cathode, imagine it is a low potential energy, and as we see a anode, imagine it as a high potential energy. Okay, as E always flow from high potential energy to low potential energy, as we saw, like electric field lines are going from positive charges to the negative charges, and when I say positive, you must think it is an high potential energy. So you can say we can replace the positive and negative charge with high potential energy and low potential energy. So we can say this, that electric field lines flows from high potential energy to low potential energy. So let's jump into the next slide. The first point is, where E exists, there must be existence of difference between potential energy. So let's take an example of battery. So we have the anode of the battery and the cathode of the battery. We know the electric field lines goes from anode to cathode, okay, from this direction, anode to cathode. So let's think that when we have higher potential energy and we have lower potential energy, in between we will have electric field lines from higher potential energy to lower potential energy. Let's think it in reverse. We have an electric field, it's heading towards this side. So you will get to understand that it was developed by some kind of potential difference. So it must be low potential here and high potential here, isn't it? So that's it. Let's have a look on the PPT. We have battery. This is the positive terminal, which is anode, and this is the negative terminal, which is cathode. So we are saying, if an electric field line is present in the system, there must be a potential difference in this system. You get it? Okay. So we are going to the next point. If we consider a charge with value 1 unit and also consider another charge of value q unit, the potential energy difference generated between them is known as potential difference. It's similar to EMF. Okay. So let's take an example. We have a positive charge that's value is q, and we have a negative charge that's value is 1. Okay, there must be a potential difference in the system. Obviously there will be. So the electric field lines will go from positive to negative. The potential energy difference in this system can be considered as potential difference, or can be considered as voltage difference. So whenever we have a q valued charge and a 1 unit charge, then we can consider this potential energy of the whole system as potential difference or voltage difference. You can say it as EMF also, though EMF is a little bit different, but you can consider it same because the quantity is kind of similar. Okay, so let's move forward. Now we have resistors. Now we are getting in our territory. So let's have an analogy here. This is the hill and water is coming from the top of the hill to the bottom of the hill. Why it's coming this way? Let's think. Whenever we move upward, we gain potential energy. That means we are gaining potential energy. When we are here, the potential energy, let's suppose it's 0. When we go up h height, from here to here, the potential energy becomes mgh. It becomes higher. So with a little bit of force, we can just make something flow from higher potential energy to lower potential energy through a ramp. As in the example, you can see we have water molecules here, and with some little bit of force we can move them down along the hill. So at this area the potential energy is much high, which is mgh, and at this area the potential energy is much low, tends to 0. So the water molecules tries to achieve minimum potential energy. The water molecules try to achieve minimum potential energy through reducing their height from the ground. Okay, so thus the water flows from top of the hill to ground level, and the rocks hinder the water flow. What does it mean? Let's imagine we have a hill here and water molecules are sliding or falling from the top of the hill to the ground level through a ramp, and at that ramp we place some stones. What will happen? Water molecules will try to flow from this ramp and it will bump into those rocks, and the rocks will hinder the water flow, isn't it? The rocks will try to resist the water flow. So it's working as a resistor. You get it? So let's move to the circuit part. As you can see, we have a circuit here. It is battery, it is positive terminal which is anode, and it is negative terminal which is cathode, and the current is flowing from anode to cathode through the wire, and at the wire we have a jittery path. You can say this is resistor. This is the symbol of resistor, and after that we got LED. So what I am trying to say, when current or positive charges flows from higher potential energy to the lower potential energy through the wire, the resistor tries to resist the current. It can't nullify the current, but it tries to resist the current. It just adds a little bit of resistance to the circuit. Okay, so resistor, what does resistor do? It resists the flow of current. Okay, so what's the conclusion? Current flows from anode to cathode. We know it very well, and resistor try to resist the current flow. Okay, so let's go to the next slide. Now capacitor, these are very interesting. So we have an analogy here also. So let's see, we have something called shishi odoshi. It's very famous in Japan. We have a bamboo structure here, and from which water flows into another bamboo structure which is pivoted to some point. Water flows from a bamboo structure to another bamboo structure. Water flows from a bamboo structure to another bamboo structure. This bamboo structure holds the water for some times until some certain conditions are fulfilled, like until it get fulfilled. Until then it holds the water, and when it gets filled with water, it just drops the water to another pot. You get it? Here you can see the water is flowing, and this segment of bamboo acting as a container until certain conditions are fulfilled. What are those certain conditions? Until it gets filled with water. Okay, so and you can see once it is full, it emits all the water inside using its potential energy advantage. Obviously bamboo, which is the initial bamboo is fixed here. From there water is flowing into the second part of the bamboo, and once it gets filled with water, it just drops the water to another pot. So you can see we have potential energy higher at this position, and once it drops, it lowers its potential energy. You get it? Okay. So through this analogy we are trying to understand capacitors. So let's move forward to the next slide. And here you can see we have another circuit. We have a battery right here, and it is the, again it is the cathode, it is the cathode and it is the anode. Okay, we got resistors here and a capacitor here. It is the symbol of capacitor. Two parallel rods. Okay, so what is happening in this circuit? The battery has positive terminal which has higher potential energy, and it has also negative terminal which has lower potential energy. So the positive charges flow from higher potential energy to the lower potential energy by the circuit. So once the positive charges from the positive terminal tries to go across the circuit and go towards the negative terminal, it encounters the capacitor, and at this position you can see there is no circuit, no wire, so the charges can't pass, isn't it? So the charges can't pass, they just accumulate there, creating there another potential energy. Let's assume this is a battery, it is the anode. From the anode a circuit is going to the cathode, and in that circuit we have parallel plate capacitors. Once positive charges are leaving from this anode part of the battery, it reaches to the one plate of the capacitor, and it can't go through this because it is insulated, it is there is no wire in between this, so it accumulates here. And as you know, we can say the positive charge is going from higher potential to lower potential through the wire. But similarly, we can also say the electrons from the anode goes to the higher potential through the wire, isn't it? The negative part, which is cathode, has lower potential. So electrons are moving from lower potential to higher potential through the wire, and thus they move the opposite direction as the current. It will also encounter a capacitor, but it will encounter the other part of the capacitor, and it will accumulate itself in that part of capacitor. So imagine this is a capacitor, we will have positive charges stored here and negative charges stored here, creating another potential energy difference. So the current flows through them, acting as a container that stores electrical energy. Obviously it will be electrical energy, we can say potential energy. Energy is interconvertible until certain conditions are fulfilled. Okay, now we are talking about conditions. So once the capacitor is fully charged, we modify the circuit. Okay, we modify the circuit, but how? We just remove the battery. You can see there is no battery here. We are just removing the battery. Once we remove the battery and connect the resistor to the circuit, to the capacitor through wires, at that position the capacitor has higher potential energy left side and lower potential energy right side, isn't it? The positive charge accumulated here and the negative charge accumulated here, you remember? Okay, so from this the capacitor will act like a battery itself. So the positive charges will run through the circuit and go to the negative plate of that capacitor. A current will flow. Now it has electrical energy. At the initial time the capacitor was not charged. There wasn't any charge present in those plates of the capacitor. But once we charge the capacitor, we get the positive charges accumulated here and the negative charges accumulated here. So we got a potential difference in between them. Then it will work as a battery and it will generate electricity, and yeah, rest you get it right, obviously. Okay, so what's the conclusion? The conclusion here, the capacitor stores electrical energy. Obviously, it stores. So let's move to the next part. Now we have another interesting topic, which is inductor. So how to explain an inductor? What is inductor and how to explain one? At first, imagine inductor as a stubborn kid who just does opposite to the instruction. So let's just have a look. This is the symbol of an inductor. So as the analogy said, inductor is a stubborn kid. By applying the analogy, we can get, if current is rising in a circuit, inductor will try to decrease that current, and if current is decreasing in a circuit, the inductor will try to increase that. So actually inductor opposes the cause of the current flow. Anything that causes the current flow to change, it opposes that. Let's take a look. We have a circuit here. Here is a battery, you can see, and we got a resistor here, an LED here, and a switch here. Once we close the switch, the circuit is closed and current will flow, and once we open the circuit is open, the current cannot flow through the wire because it's not connected. And here we got an inductor. So let's think about it. The switch is off initially, and once the switch is on, what is happening? Once the switch is on, the battery, the positive terminal of the battery, from the positive terminal of the battery, the positive charges leaves to a journey. Obviously, you know, we have repeated it so many times. So from the positive terminal of the battery, positive charges goes through the circuit and come back to the negative plate of that battery. Okay. So once it reaches to the inductor initially inductor wasn't facing any current flow, so there wasn't any current flow, and now at the moment when inductor encounters the current flow, it sees the current is flowing. Why shouldn't we oppose it? It tries to say that. So it creates an EMF. Now we are talking about EMF, which is a potential difference, kind of. You can say it as a potential difference. So it creates an EMF, it creates another battery inside it to the opposite polarity of that initial battery we had discussed in the circuit. Like we had discussed in the circuit, this battery, but here the inductor at the initial point will create another battery like this, positive and negative. From this scenario, the positive charges will try to move there, and from this battery the positive charges will try to move towards the inductor, and for the inductor's induced EMF, the positive charges will try to move away from the inductor. You see, the current flow is decreasing, as if, just imagine if we we discard the inductor from this circuit, so we will be left with just battery. So there won't be any issue. The battery will release its positive charges and it will travel through the entire circuit and reach to the cathode part of that battery. But once we introduced an inductor here, what will happen? Inductor will create another battery like like this. Inductor will create another battery like this. Okay, positive, negative, positive, negative. It is an inductor. It is an inductor which is creating its own EMF, own potential energy difference. So for the inductor, the positive charges will try to move this way, but for the battery, the positive charges will try to move this way. So there will be a opposition in between the battery and the induced EMF. So the expected current was, let's suppose the expected current was 10 ampere, but due to those induced EMF, the current value will decrease, and let's say it will decrease up to a certain level, like 2 ampere it will decrease. So the net current flow will become 8 ampere. You get it? How fascinating. Once the switch is on, the intensity of the light from LED gradually increases up to max. It gradually increases. When the inductor encounters the current, it will try to decrease it, but it can't decrease it. Like, it can't decrease it all the time, na? The battery has upper hand, so it can't decrease it all the time. It will eventually glows up to max. So let's suppose we have an LED in this circuit. We have an LED in this circuit. It will glow with a dim intensity. After some time, it will glow up to max intensity, and the similar case will appear once we switch off the circuit. Once we switch off the circuit, the battery will be disconnected, and there will not be any current flow. So at that scenario, the current flow is decreasing, isn't it? The current flow is decreasing. So the inductor will try to increase that current flow, and it will generate another EMF which will be similar to the polarity of battery, like this. To increase that current flow, it will try to create a same polarity EMF in the circuit. So when we switch off the circuit, the intensity of the light from LED gradually dims till null. Until the LED is completely turned off, it will gradually dims. It will not just go like this, that you switch on the circuit and it glows. No, it will gradually increase its intensity, and once you switch off the circuit, it turns off. No, it gradually dims and eventually turns off. You get it? That's how inductor works. So let's move to the next part. Now we have another fascinating thing, which is diode. Diode is basically, you can say, the heart of computers. You can say it. Like, let's see what diode does. Diode actually allows current to flow strictly in one direction. Okay, strictly in one direction. What does it mean? It means if we insert a diode in a circuit, it will maintain the electric current flow to a particular direction. Let's suppose we have a circuit here, a battery here, a resistor here, and a LED here, and we introduce a diode in between that resistor and battery. So we allowed the path that the current can flow from this to this, from the positive terminal to the negative terminal. But what if we reverse the polarity of battery? We connect the positive terminal here and the negative terminal here. It won't enlight the LED. due to the diode. The diode strictly allows the current to flow from this to this direction, not this to this. You get it? Okay, let's jump into this. This is very interesting topic. Okay, so we have two type of diode. Like one is primitive diode, which are also known as vacuum tubes. These vacuum tubes are really heart of early computers. Obviously, we will jump into that. But we have another type of diodes, which are modern diodes. So why need to study vacuum tubes? Aren't they old? Obviously, they are old. They are rarely used in recent techs, modern techs. So why are we even bothered about this? Let's see. We have early computers. To understand how those early computers work, we must need to know about vacuum tubes. Without knowing vacuum tubes, we can't understand how the computers are even working till now. We can't even say that how the computers are working now. And without understanding the history, we can't move forward, isn't it? So let's go and learn about vacuum tubes. So vacuum tubes, they are based on phenomenon like a phenomenon called thermionic emission. A new term, thermionic emission. Kind of scary, na? But it's not. Let me tell you, it's not. Imagine a metal plate here, and we heat the metal plate. Once we are heating it, it loses electron. The emission of electron from a heated metal plate is known as thermionic emission. Isn't it simple? Let me tell you again. We have a metal plate right here and we are heating it. Once we are heating the metal plate, from the metal plate, electrons are moving outwards. Electrons are getting radiated. That particular phenomenon is called as thermionic emission.
So we have discussed about thermionic emission. Now let's have a look at this circuit. At this circuit, you can see the anode plate is connected to the anode part of the battery, and the cathode plate is connected to the cathode part of the battery. So what we are doing here, to create a vacuum tube, we heat the cathode plate. On heating the cathode plate radiates its electrons, or loses its electrons, and those electrons are getting attracted towards the anode plate, and thus the electron flow happens. Once the electron flow is happening, we can say the positive charges flows opposite to the electrons, and hence the current is getting flowed in the circuit, and it is strictly in one direction, because let's say the cathode radiates electrons and those electrons are free at that time, but due to that, electric field lines from the anode to the cathode, the electron will feel force that will be opposite to the electric field lines. The electric field lines will go from anode to cathode, and the electron will feel force from like towards the anode. It will be attracted towards the anode. So the electron will be attracted towards the anode, and it will flow in only that direction. There will not be any other direction the electron will be going. Okay, so electron will be going in only cathode to anode, forming a unidirectional flow. Thus it will act as a diode. So it's vacuum tube. This is the setup of vacuum tube. Now we are talking about triodes. You can imagine triodes as switches. Like What is switch? When we turn it on, it closes the circuit, and when we turn it off, it opens the circuit. Okay, so let's have a look here. If we introduce a cathode net just in between the anode plate and the cathode plate, the anode plate, the cathode plate, and in between we introduce a mesh, a net of cathode. Like when the cathode is just there with zero potential energy, it will be acting just like a metal net, nothing else. So at that case, the cathode will radiate electrons and it will be attracted towards anode. It's totally simple as we have seen. But when those net have low potential in it, then the electron will be radiated. But due to that low potential, electron will not be attracted towards that low potential. It will try to go away from the low potential. Hence, the electron will not be attracted towards the low potential, it will try to go away from the low potential. So, the electron flow towards the anode plate will not be happening, isn't it? Will not be happening. Like once we heat the cathode plate, it will radiate electrons, and we have cathode mesh here, like cathode net here, and which is low potential. Electron will move away from the low potential, so the electron will not slip through the mesh and go towards the anode. Electron will not be flowing through the circuit. Hence, the positive charges will also not be flowing through the circuit. We can say the current will not be there. So once we introduce low potential at that mesh, at that cathode mesh, it will turn off the circuit. And if we introduce zero potential at that cathode mesh, then it will be closing the circuit, making all the circuit elements turned on. So let's move forward. Now we have modern diode. These are made of semiconductors. Okay, now we have reached the point where we are introducing you to semiconductor. Like what is semiconductor? Semiconductor is silicon plus little bit of trivalent or pentavalent atom. Let's have a look. Like we have a group of silicon atoms, and in that if we add a little bit of trivalent atoms or little bit of pentavalent atoms. What are trivalent atoms? Trivalent atoms are boron family members, and pentavalent atoms are nitrogen family members. So if we add just a little bit amount of them, then we get a material that is known as semiconductor. So semiconductors are of two types. On addition of trivalent atom, we get p type semiconductor, and on addition of pentavalent atom, we get n type of semiconductor. Why p type and why n type? P stands for positive and n stands for negative. Okay, so why positive and why negative? Okay, let me just explain it. Let's assume we have a p type semiconductor here. In that p type semiconductor, we added trivalent atom, so it will lack a little bit of electrons. So the lack of electrons, we call it hole. We consider those holes as positive charges. So there will be majority of positive charges, there will be more positive charges in p type semiconductor. And as we take n type semiconductor, it will be filled with some pentavalent impurities, so it will have more electrons. As more electrons, we can say electrons are the majority in this semiconductor, and at p type semiconductor, holes are the majorities. We can say positive charges are the majorities. Okay, so now how the modern diodes are formed. This is the interesting part actually. We just keep p-type semiconductor and n-type semiconductor side by side, forming a modern diode. Like a p-type semiconductor and a n-type semiconductor are sitting side by side, and the system is called as modern diode. Okay, how does it work? Let's have a look. The p-type semiconductor has positive charges as majorities. These black balls are positive charges, and the red balls are negative charges. The red balls are negative charges. So at first, imagine this was the case. There are positive charges and negative charges as well. Due to let's just focus at this region. At this region, we have positive charges and negative charges just sitting side by side. Will be there any attraction? Obviously there will be an attraction, and due to that attraction, the positive charges, wait, let me just change the color. Okay, the positive charges, it's not visible. Okay, the positive charges will be shifted towards the negative charge, and the negative charges will be shifted towards the positive charge. Okay, so there will be an interchange in the junction, and it is known as depletion layer. Here, as you can see here, the positive charges due to attraction is getting replaced, and the negative charges due to attraction is also getting replaced. Okay, forming a depletion layer. As you can see, the positive charges are present here and negative charges are present here, so the electric field line will be positive to negative. We have discussed it so many times. Okay, now we have a question, like we have electric field lines in that depletion layer. That means there must be potential difference. Yeah, obviously there must be potential difference. And if there is potential difference, current must flow. Yes, but here current won't flow. Here's the reason. The majority conductor in the p-type semiconductors will be positive charges, but there will also be minority conductors, which are electrons. They will move from p-type to n-type, obviously, and the n-type has electrons as majority conductors and positive charges are minority conductors. Due to that electric field, the positive charges will be flowing this way, balancing the whole depletion layer. You get it? Due to attraction, the positive charges was shifted towards the negative charges, but due to the flow of electric field lines they made, due to the potential difference they made, the minority charges are flowing, balancing the whole system. You get it? That's why on forming a diode, like making those p-type semiconductors and n-type semiconductors sit side by side, it won't flow any current until you give it an external supply. A battery will be required for that reason. So yeah, we have discussed about modern diodes. Now let's jump into, okay, we have further explanations. Like now we have considering we are considering external batteries. In this scenario, we have external battery. The anode side is this and the cathode side is this, and due to this battery an external electric field will be there, okay, which will be opposite to the internal electric field. The internal electric field is so small and the external electric field is so large. Due to this reason, there will be no chance that it will stop the current from flowing. Let's see. The positive charges will be flowing in this direction, and at this region the positive charge won't be crossing this depletion layer. The positive charges won't be crossing this depletion layer, but we got a support from the external battery. Due to that support, due to that external battery's uh, electric field lines, or you can say the potential difference is much larger than the internal potential difference in between the diodes, it will make it across the n type semiconductor and will eventually go towards the cathode of the battery. And this scenario is called as forward biased, where we connect the anode of the battery towards the p type semiconductor and the cathode of the battery towards the n type semiconductor. We get it as forward biased condition. In this scenario, a large external electric field opposite to the direction of electric field in internal electric field, depletion layer will be negligible thickness. Depletion layer will be of negligible thickness. Like the depletion layer will be so thin that a positive charge can easily cross it. This condition is known as forward biased condition. Okay, so now we'll be discussing about the reverse biased condition. We have studied the forward biased condition, which is p type semiconductor attached towards the anode of the battery and n type semiconductor attached towards the cathode and the battery. This condition was forward biased condition. And now we are going to talk about reverse biased condition. In reverse biased condition, as the name suggests, it's just swapping the polarity of battery. Like a diode is here, p type semiconductor, n type semiconductor, and the p type semiconductor is connected to the cathode part and n type semiconductor is connected to the anode part. So n type is connected to the anode part, which is positive, and p type semiconductor is connected to the negative terminal of battery, which is cathode. Okay, let's see. So yeah, in this case we will be having E external, that is external electric field due to battery, and E internal, that is internal electric field in that diode. The both will be in the same direction. For this reason, the depletion layer will be larger, will become much more thick than in forward biased. In forward biased, we have seen that the depletion layer becomes much more thin, and in reverse bias condition, due to the external electric field getting aligned with the internal electric field of the diode, the depletion layer becomes much more thick. So let's see. In this reverse bias condition, due to having external electric field in the same direction as internal electric field, depletion layer will become more thick, hence almost no current will be flowing. Obviously, if the depletion layer becomes more thick, that means much larger resistance it will provide for the current flow. Okay, but after certain value of V external, current starts flowing due to the flow of minority electrons. So let's see. We know Joule's law, right? Okay, let me just cover it up. Joule's law says if we flow a current through a wire up to a certain time or up to a certain limit, the wire will tend to emit heat energies, and this is Joule's law. So in the diode, once we arrange the diode in reverse bias condition, after a certain time it will get heat up, and once it gets heat up, the minority electrons present in the p type semiconductor will start moving towards the n type semiconductor, and minority of the n type semiconductor, that are holes, will move towards the p type semiconductor, and there will be a flow of electron. And uh, when we get flow of electron, there must be a current flow in the circuit. So it happens due to the temperature rise. Okay, so yeah, that is reverse bias condition. Now let's move to the next slide. Now we have transistors. Yeah, these are so much important. Okay, so transistors are also made up with semiconductor materials. There are two types of transistors, as you can see, NPN transistors and PNP transistors. You may notice that NPN means n-type semiconductor, p-type semiconductor, and then again n-type semiconductor. A p-type semiconductor is in between two n-type semiconductors. This setup is known as NPN transistor, and the reverse of this, like an p-type semiconductor, n-type semiconductor, and again a p-type semiconductor. So we can say an n-type semiconductor is sitting in between two p-type semiconductors. This is the setup of PNP transistors. Okay, let's see. This is the symbol of transistors. Like we have base. Okay, don't bother. Base, emitter, and collector will be discussed soon. So let's say it's a base and it's a collector connected to the base, and we have emitter connected to the base as well. This is the basic setup. If we talk about NPN, then the symbol becomes a little bit different, and if we talk about PNP, the symbol will also become a little bit different. We will talk about it as working of this NPN transistors and PNP transistors are a little bit different. So let's see. In NPN transistors, if we have base to emitter, like, oh, at first I have to mention base and emitter. What are those? So let's have a look at the structure of NPN transistors. So it is n-type semiconductor, after that we have p-type semiconductor, and after that we have n-type semiconductor again. So add those end semiconductors, like n-type semiconductors, we say one as collector and one as emitter. Okay, and at the middle we have base. In PNP transistors, we have p-type semiconductors at both the sides and n-type semiconductors in between them. So we name a p-type semiconductor as collector, another p-type semiconductor as emitter, and in between the n-type semiconductor is base. Okay, so now Let's have a look how they work actually. So we have base here, we have collector here, and we have emitter here. Okay, so for NPN transistors, I am talking about NPN transistor. So for NPN transistors, if we have a little bit of current flowing from base to emitter, if we have little bit of current flowing from base to emitter means P and N. Okay, let's visualize it. N, P, N semiconductors. Like as I said, it's collector, it's base, it's emitter. If we have a little bit of current flowing from the base towards the emitter, then a large current will flow from collector to the emitter. Okay, like if a little bit current flows from the base to the emitter, a larger current will be flowing from the collector to the emitter. So the symbol becomes like this. Okay, and in the case of PNP, let's talk about PNP as well. In the case of PNP, we have base, collector, and emitter, and in this case, how the PNP transistors work, like if we have a little bit of current flowing from emitter to base. Okay, now visualize it again. PNP. Okay, collector, base, emitter. Okay, if we have little bit current flowing from the emitter to the base, a larger current will be flowing from the emitter to the collector. It's just a kind of reverse. Okay, just have a look. PNP. If we have a little bit current flowing from the emitter to the base, a larger current will be flowing from the emitter to the collector. Okay, it's working of PNP transistor. So if a small current flows from the emitter to the base, a larger current will be flowing from the emitter to the collector. That's the working of PNP transistor. And here you can see we have designed with just the condition, we have obtained the symbol of PNP and NPN as well. It is PNP and NPN as well. So these are current regulated transistors. As you have seen, I am talking about the current flow, a little bit current flow of from base to emitter or emitter to base. I was talking about little bit current flowing from base to emitter or emitter to base. So it's a current regulated. So these transistors like NPN transistors and PNP transistors are current regulated transistors, also known as BJT, bipolar junction transistors. Okay, so moving on, we have another type of transistor, which is MOSFET, metal oxide semiconductor field effect transistor. No need to remember, but yeah, these are voltage regulated transistors. Unlike the BJTs are current regulated transistors. MOSFETs are voltage regulated transistors. How they work? Let's see. This is the symbol where we say base as gate and collector as you can say collector as drain and source as, wait, let me just undo it. Okay, source as emitter as source. So what I was talking about, at this symbol you can see that base is represented as gate and collector is represented as drain and emitter is represented as source. So we have just modified those names, nothing else. So let's have a look. It is the basic symbol of MOSFET transistors. How they work actually? Its working is very simple. Like if we have a little bit of potential difference, excuse me, if we have a little bit of voltage difference between the gate, which is base, and the source, which is emitter, if we have little bit of voltage difference in between them, base and emitter, then there will be a larger voltage difference developed within the drain and the source. You get it? Let me repeat it. If we have a little bit of voltage difference between the gate and the source, you can say as the base and emitter, you will have a larger voltage difference developed in between the drain and the source. You get it? Okay. We will be discussing it further as well. Like, let's see. For the basic working, the V gate source regulated V drain source. Okay. Like as we mentioned, the V drain to source voltage difference from drain to source, voltage difference between them, drain to source, depends on the voltage difference between gate and source. Okay, and after that we have V gate and source attracts charges. Obviously, V gate and source, the voltage difference between gate and source attract charges. If it attracts positive charges, we say it as PMOS transistor, and if it attracts negative charges, we say it as NMOS transistors. Okay, we'll go further, don't worry. Let's go to the next slide. Okay, so we have PMOS transistors here. We have gate here, source here, and drain here. Okay, if we have a little bit of voltage difference between gate and source, we will have a larger voltage difference developed within source and drain. Okay, so let's take VGS. GS means the voltage difference between gate and source as input. If the VGS becomes 0 volt, like there is no voltage difference between gate and source, there is no voltage difference between gate and source, so there will not be any voltage difference developed in drain and source. Obviously there will not be any voltage difference developed in between drain and source, so there will not be any current flow between drain and source. And as VGS is not equal to 0, let's suppose if VGS is not equal to 0, that means V gate and V source will have difference in their voltages. Okay, so if we have a system where VGS is not equal to 0, that means it will develop a further or large voltage difference in between gate in between drain and source, connecting both drain and source together, and it will flow current. Okay, so let's move on. Now we have NMOS. NMOS, it's also same. We have gate here, source here, and drain here. If we have a little bit of, again the same, if we have a little bit of voltage difference in between the gate and the source, there will be a larger voltage difference generated between the drain and the source. Okay, so again that is it. So VGS, we are taking VGS as input, and if VGS is equal to 0, again the same, if VGS is equal to 0, that means if the gate voltage and the source voltage are the same, that means there is no voltage difference between the gate and the source. So there will not be any voltage difference formation between drain and source, so there will not be any connection formed, and the current will not flow between drain and source. Okay, again we have VGS is not equal to 0. Like once we assume that VGS, that means the voltage difference of between gate and source is present there, that means the drain and source will be connected, and there will be voltage difference in between them, and a current will flow. Okay, you may assume it like a switch, like when the voltage difference is present there, then the switch is connected, and when the voltage difference is not present there, like is not present in gate and source, then the circuit between drain and source will be open. Okay, so let's move forward again. Okay, so congratulations, you have completed part 1 of this demo session. What you have learned? You have learned some basic concepts like electric field and how the charges act in external electric fields, and you get to know about potential energies, resistors, capacitors, inductors, transistors, diodes. We have discussed about vacuum tubes, modern diodes and how they actually work. We have discussed about transistors. We have two type of transistors, BJT and MOSFET. We have discussed both of them. So now we'll be moving on to the next part of our demo session. So yep, let's roll into it. Now we have logic gates. Yeah, logic gates. These are logical components that are base of forming digital circuits. Okay, just keep those complicated definitions aside. It's a way to convey logical explanations. Okay, logic gates are a way to convey logical explanations. Okay, it's also fundamental unit of digital circuits. Yeah, as I mentioned earlier, it's also a fundamental unit of digital circuits. So there are three types of logic gates. One is functional logic gate, another is universal logic gate, and another is exclusive logic gates. So we will be discussing about just only the functional logic gates here. So in the functional logic gates, we are having NOT gates, OR gates, and AND gates, and AND gates. We had we have NOT gate, OR gate, AND gate. Okay. In universal logic gates, we are having NOR gate and NAND gate. And exclusive logic gates has XOR gate and XNOR gate. Now the question is, why these logic gates like NOT, OR, and AND are called as functional logic gates? There is a reason behind this. Actually, if we try to build any logical explanations, we must need some fundamentals. Those fundamentals are this OR gate, AND gate, and NOT gate. We can make any logical statement with OR, AND, and NOT with these three components. Now we are going towards universal logic gates. So why does these logic gates are known as universal logic gates? So these logic gates are universal logic gates because with NOR gate or with NAND gate, you can design any logics, literally any logics. You can design any logical explanations with NOR gate or NAND gate. You don't need both of them. You can just use one and create any logical explanations out there. If you use NOR, you can create any logical explanations, and if you use NAND, you can also make any kind of logical explanations out there. And there are exclusive logic gates. These are just versions of exclusive OR and exclusive NORs. Okay, so let's move forward. As we have mentioned that we are going to discuss only functional logic gates in this demo session. So here we are having a look here on the functional logic gates. We have NOT gates, OR gates, and AND gates. So yeah, what is a NOT gate? NOT gate actually, you can imagine NOT gate as a person who always tells lie. Okay, you can imagine NOT gate as a person who always tells lie. Let's see how NOT gate works. Like if someone says a true statement and you pass through the statement that statement through NOT gate. Let's suppose someone says a true statement and you pass the statement through NOT gate, then the output will become false. It lies. Okay, then if you give input as false statement, the NOT gate will convert it as true statement. By the way, as we are talking about, we will be talking about binary number system. So there we will be discussing as true equal to 1 and false equal to 0. If we say 0, it means false, and if we say 1, it means true. Okay, so similarly, if we pass 1 as input to the NOT gate, it will become 0 as output. If we give input as 0 to the NOT gate, it will become 1 as output. Okay, so this is NOT gate. This is the function of NOT gate. It just complements the input, or you can say it just reverses the input. It acts as an inverter, uh, not that inverter which enlightens the whole home supply, but the inverter that just makes it reverse. Okay, so yeah, now we have OR gate. We have discussed about NOT gate. As you can see, if we give input as true, the output will become false, and if we give input as false, the output will become true. Okay, so now we are talking about OR gates. To discuss the OR gate, there is a question you can ask to identify if it is an OR gate or not. The question is any of A or B true? Okay, let's just have a look at this truth table. Okay, by the way, this table where we demonstrate input and output of a particular gate is known as truth table. Okay, truth table. I am writing it here, truth table. It's truth table. Okay, so for OR gate we have two inputs. In case of NOT gate, we had only one input. We had only one statement, and NOT gate used to convert it it's complementary. Okay, so at OR gate we have two inputs. Let's give them names as A and B. Now the question is, OR finds if any of A or B is true or not, or finds any one of them is true or not. Okay, so the question is, let's suppose we have input true here and true here as well, like true for A and true for B as well. So the OR gate will ask, is any of A or B true? Then we will say yes, obviously both are true. Then the output will also be true. Okay, if now the second term, if A is true but B is false, then the OR gate will again ask, is any of A or B true? Then we will answer yes, A is true. Then the output will also become true. The third input, we are taking A as false and B as true. In this case also, OR will ask us, is any of A or B true? We will say obviously the B is true. So the output will become true. And the last case, where A is also false and B is also false. In this case, we will OR will ask us the same question, is any of A or B true? We will answer no, none of them are true. So the output will become false. Okay, so this is OR gate. This is all about OR gate. You can interchange true with 1 and false with 0 in any of logic gate systems. Now we are talking about AND gate. AND gate has its own question to ask. Are both of A and B true? Okay, are both of A and B true? Let's jump into the examples. We have two inputs, A and B, similar to OR gate. At the first example, we have A as true and B as also true. So AND gate will ask us, are both of A and B true? We will say yes, both of them are true. So output will become also true. For the second input, the A is true and B is false. Or now the AND gate will again ask us, are both of A and B true? We will say no, because the B is false. So the output will also be false. Okay. Now again A becomes false and B becomes true. In this case, AND gate will again ask us, are both of A and B true? Then we will say no, because the A input is false now. The output will also become false. Okay. Now both of A and B are false. In this case, AND gate will again ask us, are both of A and B true? We will say no, both of them are false. In this case also, the output will also become false. So this is all about AND gate, OR gate and NOT gate. Okay, moving forward. Now we are here, analog circuit and digital circuit. What is analog circuit? Circuits made with basic electrical components are known as analog circuits. Aren't we familiar with analog circuits? Yeah, we are. Till now, what circuits we have drawn? Those are analog circuits. Like every circuits are made up of basic electrical components. Till now, all those circuits are analog circuits. Like every circuits which are made with basic electrical components like resistors, capacitors, inductors, diode and transistors, all of them are analog circuit. Okay, now what is digital circuit? Logical circuits made with logic gates are known as digital circuit. Okay. Now logical circuits, any logical statements, if we made it with logic gates, it becomes a circuit, and that circuit is called digital circuit. Okay, like you have a logical explanation or a logical statement, you use logic gates to make it a circuit, and that circuit becomes digital circuit. It is digital circuit is a logical circuit. It doesn't have any physical appearance. Even logic gates are also logical components, basic logical components, you can say. Those lack physical existence. They are only existing in logical world. Like you can say, you can make any logical component, any logical statement with those logical components, but you can't physically arrange them to make one. Okay, digital circuit and logic gates lack physical existence. Okay, but analog circuit is real circuits we used in day-to-day lives. Now the question is, logic gate are not physical, so the digital circuit don't have physical existence, as we have talked. So why do we need digital circuits? Okay, now this is a crucial point. Why do we need digital circuits? There are so many reasons, so many reasons. Actually, there are so many reasons to switch digital. Like I am wearing an analog watch, but you can see nowadays many people wear digital watches. We have digital calculators, we have mobiles, we have computers, everything work on digitally actually. Now the case is, why digital? because digital circuit tends to preserve data more accurately and for a long term. It is the main reason. It is the main reason to switch digital. Uh, let's suppose we we are recording a song manually. Manually means analogous, and digitally. We have some tape records. We are recording a song digitally and manually. The manual record will eventually degrade, but the digital records won't degrade. Like after 1,000 years, you can still the digital records as the first date, but after 1,000 days or 1,000 years, you can't even consider the analog records because they will be degraded. So this is the main reason why we shift towards digital circuits. uh, there will be further more explanation to it in the course, but for now let's keep it simple. So congratulations, you have completed the part 2. In the part 2 you get to learn about logic gates, more about the functional logic gates and analog circuits and digital circuits as well. So now let's move forward.
Now we have reached the point where we will be discussing the components of computer, like the hardware components of computer. What is computer? Computer is just a device with hardware and software interacting with each other. This is the basic definition of computer. And what are the functionalities of the computer? The computer can take input, process some operations, and store data, and also give the output. There are four major functionalities of the computer. First, taking input. Second, performing some operations. Third, storing some data. And also fourth, giving the output. Okay, these are the four functionalities of the computer. Now let's have a look what are the components of computers. Computer have main four components and two minor components. Those main four components are input unit, processing unit, memory unit, and output unit. Those are the units are named basically just with analogy of these four functionalities: input unit, processing unit, memory unit, and output unit. Okay, and there are two minor components of computer. These are motherboard and PSU. PSU means power supply unit. Without these two, the computer cannot function. Okay, let's have a look how they are interconnected with each other. Let's say we have user here giving input to the input unit. After that, the input unit stores the data to the memory unit. After storing the data to the memory unit, the data passes to the CPU for further processing or further operations. After doing the operation, the result will be passed to the output unit. And the output unit will display the data to us or display the output to us. This is basically the data flow. Like I am a user, I am giving input to the input unit, The input unit transfers the data to memory unit or stores the data to the memory unit, and from the memory unit CPU accesses the data. From the memory unit CPU accesses the data, and after accessing the data it performs some tasks, some operations on it. After completing those operations it may store it again to the memory unit, or the result that after processing those operations on the input data, the result will be given to the output unit, and the output unit will display the result to us. This is basically the main data flow of computer. Okay, so take a screenshot of this. Okay, so moving forward, so input unit, as the name suggests, input unit is there to take input from user. Let me give an example. Like, imagine if you are giving a data to computer, so you are interacting with input unit only. Just you are interacting just only with input unit. So input unit is taking data from you. Okay, and the data that input unit takes, the data is stored in the main memory. Okay, so this is the chart. The input unit stores the data to the main memory, and from the main memory the CPU accesses the data. Okay, after that we have output unit. Just as I said, that after you give a data, the input, you give a data to input unit, the input unit stores the data to the memory unit. From the memory unit CPU accesses the data and processes some operations, and after processing those operations the CPU stores the result to the memory unit, or gives the result to the output unit. After receiving the result from the CPU, the output unit displays the data to us, or displays the result to us. So this is actually the main flow. So the output unit is interacting with us and the CPU. Okay, so here you can see the control unit and the output unit. The chart is there. And now we have memory unit. Memory unit stores data. Okay, let's take an example. Again, we are giving some input to the input unit. The input unit stores data to the memory unit, and after the data is stored, the CPU accesses the data from the memory unit. CPU accesses the data from memory unit, and after processing or after completing some task or some operations on that data, the CPU can store it to the main memory again. So this is the flow. So main memory is interacting with two components. One is input unit and another is CPU. Okay. Here you can see the chart. Like, input unit is interacting with memory unit, and memory unit is also interacting with CPU. This is the whole scenario. And after this we have CPU itself. So CPU is the brain of the computer. It controls everything in the computer. Like, every data flow in the computer is controlled by CPU. The CPU actually interacts with memory unit and also the output unit. It has two interacting sides. Okay. You will further understand the CPU is also interacting with input units also, because the computer is taking input. The command is given to the input unit by the CPU. Imagine, the computer won't take any data until the CPU tells him to do that. Okay, so CPU has the connection to all of this. CPU has the connection to all of this, like input unit, memory unit, and also the output unit. CPU has access to all of these three major parts. Okay. Now there are three parts in CPU. One is ALU, arithmetic and logic unit, another is control unit, another is memory registers. Okay, at first we look at memory registers. At memory register, as the name suggests, it just a temporary memory in the CPU itself. Okay, main memory unit is different. In that CPU we have a temporary memory unit, a small tiny registers are there, and those registers act as temporary memory units. We have main memory unit, that is the main actually the main memory unit, the data gets stored here, but at the CPU we have tiny memory registers that actually works as a temporary memory for CPU. So what is the need of it? To be precise, to access every data from the main memory, CPU has to do transactions, like CPU has to ask the main memory to find the data, and main memory will give it to the CPU, and again for another data main CPU has to ask again to the main memory, and main memory will find it and then give it to the CPU. It is kind of hectic, but to reduce this complexity, the CPU has built-in memory inside it, but it is very tiny. So the required data will be stored at once at those memory registers, and after that whenever CPU needs it, it can just read from those memory registers. It don't have to travel to the main memory and get those data again. Okay. After that we are looking at control unit. Control unit, this unit controls every data flow in the computer, like every data flow. The data you are giving to the input unit is also being tracked by this control unit, and the data is stored at the main memory unit. It is also being controlled by the control unit. After that the data is going to the CPU for further processing or operations. It is also controlled by the control unit. After that the result is getting to the output unit, and this step is also controlled by control unit, and after that the output unit displays the data to us, that is also controlled by the control unit. Control unit follows each and every data flow in the computer, actually controls each and every data flow in the computer. Okay, so yeah, now we have ALU, arithmetic logic unit. This unit actually does those operations we are talking about. Those operations are getting performed inside of the CPU, but inside of the CPU's ALU, arithmetic logic unit. Okay, at that unit we are doing some mathematical operations or some logical operations, whatever it is getting done inside ALU. Okay, and ALU is a digital circuit. We will be talking about this in detail, but for now just remember that ALU is a digital circuit. Even the computer as whole is combination of digital circuits. It is very important, it is very crucial. Just remember it for now. We will deep dive into it in future classes. So ADC and DACs are required here. We will be deep dive into this as well, but not in this class, because you will need some, like you will have to understand continuity and discrete uh, quantities for this. So we'll be discussing it for the at the upcoming sessions. So for now, let's move on. Okay, now we have motherboard. It connects all important parts of the CPU. Like for example, we have input unit, memory unit, CPU and output unit. The motherboard connects all of this at once. And you remember those PSUs? Those PSUs are also tucked together inside motherboard. Like imagine motherboard as a board where you have just put input unit, output unit, memory unit, CPU and PSUs as well. This board is called motherboard. Okay. Now we have power supply unit. Power supply unit, that PSU is giving electricity to all the components. Like imagine PSU as a electricity receiver. So the electricity is flowing into PSU and it distributes the electricity through the motherboard to all the components. Okay. Electricity is coming, PSU is receiving those electricity and distributing it along with the interconnected networks of motherboard. Like electricity is coming, PSU is capturing it and distributing it to the every part of the motherboard, and from there each and every major parts like input unit, memory unit, CPU and output will be accessing the electricity. Okay, so now we will be talking about diagram of computer. We have discussed it as well, but let me just clear it once. From input unit, the data is getting stored in main memory. As we have discussed, from input unit, the data is getting stored in the main memory. And after getting stored in the main memory, the data can be accessed from CPU, obviously. But when the CPU is accessing the data, the CPU is taking the data and storing the data inside the memory registers in it. And for performing various tasks, the data is being taken out of the memory registers and put it inside the ALU. In that ALU, the operations are getting performed. After performing those operations, the data is again getting stored into the memory registers. After that, from the memory register, the data is getting stored or getting passed to the output unit. After getting passed to the output unit, the data is being displayed to us. Okay, so this is actually the main data flow. And we have secondary memory. Like imagine it as we are giving input, the data is getting stored into the main memory, and let's assume suppose that the main memory is full, so we need to add a secondary memory. So the data will come and go directly into the secondary memory. Okay, the data will come, main memory is full, so it just go inside the main memory, and from the main memory it just goes to the secondary memory. You get it? So when the CPU try to access the data, it need to ask the main memory, and the main memory will ask to the secondary memory, and secondary memory will give the data to the main memory, and main memory will give the data to CPU, and CPU will store the data to the memory registers of it. After storing the data, CPU will act or perform some task on it and bring it to the ALU unit, and after operating with the data, the result will be stored in the memory registers, and the result from the memory register, the result is going to be passed to output unit, and the output unit will display the result to us. This is the whole system. And the control unit in the CPU, it controls each and every part of the system, each and every part. Like control unit controls the input unit, the main memory, the secondary memory, the ALU, the registers, the memory registers, and also the output unit as well. So the control unit controls every part of computer. Okay. Yeah. So let's move forward. Now we have memory hierarchy. As I told you, if the main memory gets full, then we have secondary memory, which is larger than main memory. So let's assume we have a stack of we have a stack of memories. The larger one will be staying at the bottom and the smaller ones will stay at the top. Okay, so at the very top, the very small memory elements are registers itself. Remember those memory registers in the CPU, those registers we are talking about. After that, the cache memory is there. There is a memory named cache. So cache memory will be there. Okay, which is a little bit bigger than registers. After that, we have main memory, which is much larger than the cache. After that, we have secondary memory, which is also much larger than main memory. Okay, this is like forming a triangle of memory hierarchy. It is the memory hierarchy: registers, cache, main memory, secondary memory. After that, if secondary memory is also get full, then also get filled with data, then we have tertiary memory, that is also there. We can further increase the memory. So this is actually the memory hierarchy. Let's talk about some access time. Okay, like CPU is trying to access data, from where it can access the data faster, even fastest, from the memory registers. Obviously the CPU is trying to access data, and it will access data the fastest way from the memory registers. After that, it can access data from the cache memory, which will be little bit slower. After that, it can access from the main memory, and it will be a bit time consuming. After that, we have secondary memory. To access the secondary memory data, the CPU will have much larger time than the fetching from the main memory. The time will eventually increase. Okay, the time taking to access the data will eventually increase. So this is the memory hierarchy. Let's see. So there are registers, which are very small memories inside the CPU. After that, we have cache memory, that is larger than registers but smaller than main memory. And after that, we have main memory, that is larger than cache memory. After that, we have secondary memory, which is larger than main memory. The access time increases. Like CPU is trying to access data from each and every one. The access time, the time to access the data, will be smallest for the registers. After that, it will be cache. After that, it will be main memory, and again after that it will be secondary memory. So this is the memory hierarchy. Let's move forward. Now congratulations, you have completed part 3 as well. What have you learned in part 3? You have learned about CPU, memory hierarchy, input output system, motherboard, and power supply unit. Yeah. So now, without wasting much time, let's jump into our cool discussions. So here the cool discussion begins. Now the question is, how do computers how do you talk to your computer? Okay, how do you talk to your computer? Nice question, isn't it? To answer this question, we need to know answers of some other questions. Yeah, let's see what are those. With what electrical components hardware are made? Nice question. Hardware are made from what electrical components? How does software interact with hardware? Nice question. How does machine code interact with hardware? Okay, we have to find all of the answers of these three questions. Moving forward, the first question: with what electrical components hardware are made? Okay, hardware is just a group of electrical devices like input unit, memory unit, CPU, output unit, motherboard, PSU. Those are just basic electrical components. Yeah, as they are physical circuits, like we have discussed about analog circuits. As they are physical circuits, we can touch them, we can physically feel them, so they must be made up with analog circuits, obviously. And analog circuits are also made up with resistors, like basic electrical components: resistors, capacitors, transistors, inductors, diodes, all those basic electrical components. Now, to connect all of these components together, we must need breadboard, motherboard, or motherboard to organize the circuit together. And like we have a bunch of resistors, capacitors, inductors, transistors, diodes. Okay, we have bunch of this. Does that mean we have computer? No. We have to arrange those components in a very particular order to get a hardware device. So, in order to do that, we need breadboard or like motherboard. You will have motherboard for a smaller hardware. Inside it, you will organize each of those basic electrical components to create a CPU, or to create a memory, or to create an input unit, or to create an output unit. You will do all of this. After doing all of this, it will be considered as a single hardware component. After making the hardware component functional, you will take another motherboard and you will attach it to that motherboard, where PSU will be there. In this segment, there will not be any PSU, okay? But in this segment, there will be a PSU. You get it? In this motherboard, or in, let's say, we are making CPUs with some resistors or whatever, with basic electrical components, we are making CPU. So, to make the CPU, we must need a platform to organize those basic electrical components in order. So, we will have a motherboard type of thing, where we will attach all the basic electrical components to make a CPU. But in that CPU, we will not put any power supply unit in it. When we are assembling all those major components of computers, then we will be attaching the PSU to the motherboard. Okay? Good. So, we have the answer of the first question. So let's move to the next question. How does the software interact with hardware? Okay. We have a beautiful analogy here. Let's see. This is human and he knows English. And this is a monster who doesn't know English. Now, can they have a conversation? So the answer is, if there is no translator in between them. So let's think of me talking to a monster. I know a little bit of English, and the monster doesn't know English at all. So I am trying to make a conversation with the monster. Can I do this? Am I able to do this? No. Without a translator in between, I cannot translate my English to the language the monster understands. Okay, so I need a translator in between. If I have a translator in between, I can communicate with the monster. Okay, so similarly, human knows English, computer knows machine language. Okay, computer knows a language that is known as machine language or binary language. So we don't know machine language and binary language, or binary language, like we don't know, we have no idea that how the binary language is working. So we need a translator in between. So what it say? But wait, can't human learn the language computer speaks? Human can learn any language. Can't it learn the machine language or the binary language? The answer is no. Human can't learn those machine language or binary language up till now. Like let's give you an example that how machine language or binary language looks like. It looks like this: 0 1 0 1 0 1 1 1 1 0 1 1 0 1 1 0 0 0 1 1 1 0 1 0 0 1. This is a binary code. How can we even predict that what is going on here? We can't even predict that. So we can't actually learn the machine language or the binary language. But to avoid ambiguity, like I am speaking English, but let's say somebody asked me if I want to go outside or not. I say maybe. I am being ambiguous here. I am not clear enough. But in order to communicate with computers, I must be unambiguous and clear as crystal clear. I need to convey my feelings or my opinion to the computer directly, or there shouldn't be any ambiguity in my conversation, in our conversation. Like I cannot say maybe here. What does maybe mean? I may go or I may not, isn't it? So it is kind of ambiguous. To avoid the ambiguity, the English in the English language, we have created another language that is called programming language. Okay, we have created another language that is kind of similar to the English language, but it is unambiguous. It is crystal clear. So on creating this programming language, we learned it, and after learning it, there is translator in between. We are giving the translator what we want to tell the computer. The translator takes it and converts it to the machine language, and the computer understands it. So this is the procedure. Okay, so let's moving forward. Like as I said, human developed another type of language to remove the ambiguity from the conversation. English is ambiguous and programming language is unambiguous. So we learn programming language and give instruction to the computer from programming language or through programming language. The translator takes it and converts it to the machine language or binary language, and the computer understands those languages. Okay, so moving forward, how does machine code interact with hardware? Now the question is how the machine code interacts with hardware. As machine code or binary code written in 0 and 1, there must be digital circuit in it. Obviously there must be digital circuits in it. Like in digital circuits, if you remember, we have talked about zeros and ones. Zeros are false and ones are true. So we have talked about zeros and ones. Aren't those related to the machine code? Obviously they are. So in order to work, or in order to understand the machine code, the computer needs to work with digital signals or digital circuits. Okay, but digital circuits doesn't exist physically. There is no existence of digital circuit in physical world. So what should I do now? We will create digital circuit from scratch. We will make it exist in this world. Okay, we will make this digital circuits exist in this world. Digital circuits. Aren't logic gates the fundamental of digital circuits? Yeah, logic gates are fundamentals of digital circuits. So, are you talking about creating logic gates in this physical world? Yeah, I am talking about that. So let's create logic gate. Now we are for this demo session, actually we are just creating the NOT gate, but in the detailed lectures we will be discussing OR gate, AND gate, NAND gate, NOR gate, XOR gate and XNOR gate as well. So don't worry. Just look at the diagram. We have gate here. Just look at this part. Look at this part. Okay. Let me just change the color. Look at just only this part of the circuit. You can see we have source, gate and drain, isn't it? We have source, gate and drain. Okay, isn't it a PMOS transistor? Obviously, because we are talking about source to gate voltage difference. Let me just clear it once. Excuse me. Let's suppose we have zero voltage here, like zero voltage. We have zero voltage here in the Vin. Now the potential difference between the source and the gate becomes a little bit. That means there is a potential difference in that. After getting the potential difference, the source and drain will be connected. The source and drain will be connected and there will be a potential difference out there, isn't it? There will be a potential difference. There will be a potential difference of 5 volt. You get it? Like we have a gate here, a source here and a drain here. Drain, gate, source. The voltage difference between source and gate is there, like being the voltage of gate is 0 and the voltage of source is 5 volt, we have a difference in between them, that is 5 volt, and after getting the difference the drain and source will be connected and the output will be 1. Like we are giving 0 volt, we are giving 0 volt as input and we are getting 5 volt as output. We are getting 5 volt as output, isn't it? The source and drain is getting connected. That means this the source, the voltage of source is getting transferred to the voltage of drain, is getting transferred to the voltage of gain. So think about it this way. Due to having the difference between due to having the voltage difference between gate and source, we connected the drain and the source. So as the source voltage is 5 volt, the drain voltage will also be 5 volt. So we are giving 0 volt as input and getting 5 volt as output. Isn't it gain? Obviously it is a gain. So we can take it as output 1. We can take the output as 1. And after that, we have another NMOS. In this scenario, the gate is in 0 volt. Like the gate is here, the source is here, and the drain is here. So there is no difference, voltage difference in between gate and source of NMOS. You see, it has also 0 volt and it has also 0 volt. Having no voltage difference means there is no connection between drain and source. So the output will also be so the output doesn't matter actually. As this don't get connected, the output doesn't matter in the case of NMOS. Okay. So as you see, for the PMS, if we take the input voltage as 0 volt, or let's suppose the input is 0, then the output we get is 1. Like it is getting connected. At 0 volt input, the voltage difference is here, VGS is here, voltage difference, and due to this voltage difference, these source and drain are getting connected with each other, and the output becomes 5 volt, and the 5 volt output we are taking it as 1. For NMOS, the voltage difference between gate and source is equal to 0. So there will not be any connection developed between drain and source. Okay. So now let's move forward. Now we have voltage in as 5 volt, like input voltage as 5 volt. When we introduce input voltage as 5 volt for the PMOS, the input voltage is 5 volt at the gate and the source voltage is also 5 volt. So there is no voltage difference in between the gate and source. So at this scenario, the drain and the source will be disconnected in case of PMOS, but in case of NMOS, there will be a 5 volt input voltage at the gate and the 0 volt at the source. So there will be a 5 volt potential difference there. Due to this potential difference, there will be a connection formed between the drain and the source. So as we have given the 5 volt as input, we are connecting the source to the drain here. Now at the beginning of this explanation, we have told that the gate has 5 volt and source has 0 volt. And when the drain is connected to the source, the drain is also becoming 0 volt. So the output becomes 0. Isn't it fascinating? It is working as a NOT gate. So we have took all of the basic components and trying to make those logic gates in real life. Okay, so yeah, we'll be making OR gate, AND gate, every other gates in our detailed lectures. So make sure to check that out. So now let's backtrack. We have logic gates existing in the physical world. Now we can work with digital circuits. If we can work with digital circuits, the machine language will interact with digital circuit easily, and through a translator in between us and the computer, the machine language can be transferred into the programming language, and vice versa, the programming language can be transferred into the machine language as well. So this is the entire process, that how we are talking to the computer. Okay, so let's moving forward. Now there are more to it. This is just a demo lecture of our course, that is Let's Dive into C, as we discussed earlier. So in this course we will be teaching basics of computer architecture. This is just a tip of iceberg, literally just a tip of iceberg. So we will be discussing in depth of computer architecture, basic math required for the programming, C programming language. We will be discussing it from basic to advanced. After that we will be knowing how data are getting structured, data structure and algorithm. After that we will have some hands-on projects like developing snake game, developing tic-tac-toe, rock paper scissors, dungeon game, and the Chrome dinosaur game as well. We'll be doing all of this. Okay, this is the course syllabus. You can take a screenshot of this. We'll be discussing many more things. There are many things we'll be discussing. So I insist you to join this course. It will be beneficial for you. So we will have practical classes after each theory classes. We'll be having practical classes, and there will be doubt solving classes each Sunday. Each Sunday there will be doubt solving classes. Those doubt solving classes will be taking doubts from theory sessions and practical sessions as well. So we have two versions of this course. One is basic version and another is pro version. The basic version will not include the projects, and the pro version will have all those projects we have discussed about: the snake game, the tic-tac-toe, rock paper scissors, dungeon game, and the Chrome dinosaur as well. So the admission portal is open till 30th October, and the classes will be started from 3rd November. So there is not much time left. So you can check all of this, but there will be a large game we are developing, that is dungeon game, and we'll be uploading it to the Steam and other platforms, and it will be like we will be launching it. So it will be fun, and we will hire an intern who will score good enough in this course. Actually, we will take a final test in this course, and whoever or anyone who scores higher than the criteria, we will hire them as intern in our team. Actually, we will give them job offer in our team, and we will be discussing Git and GitHub for better management. After this, you can see the pro version and the basic version. There will be no projects in the basic version, so make sure I recommend all of you to purchase the pro version. So this is the procedure to enroll into the course. Join the WhatsApp group from the link in the video description, and fill the form up given in the WhatsApp group's description. So you have to join the WhatsApp group, and after joining that, in that group description you will see a form. So fill up the form and submit it. You will be enrolled. So thank you for your attention. Let's explore the programming world together. We'll have fun. So make sure you don't miss it out.